Today we're talking about continuity, which is when we start using limits to actually sort of differentiate two types of functions, the functions that are continuous and the functions that are not. So continuity of a function is exactly how we're going to do this. The word continuous itself, it means exactly what you would expect it to mean, right? A process that takes place without interruption. So whenever I say continuous, you can think without interruption. And we kind of hinted on that last time in the last video when we said that for polynomials and rational functions, to find the limit of f of x as x approaches a, we could just find f of a by just plugging in the point, which is what this is saying right here, right? So I said back then that not all functions would work that way, but that more than just polynomials and rational functions would work that way. And those that have this property are called continuous functions. Okay. So continuity is a local property, meaning a function is continuous at a point A if this happens. Okay, it could happen that it is continuous at A, but it is not continuous at another point. Okay, we're going to see some examples of this as we go on. Okay. Note that to say that the limit equals to f of a, there are actually three things that need to happen. Okay, and this is very important. We can just write this. We can just write this and hope that whoever is reading understands it, and that's fine. But whoever is reading this needs to think of these three different things. Whenever you say two numbers are equal, right? First, both numbers have to exist. So first of all, the limit has to exist, right? F of a has to be defined. So both sides of the equation have to exist, and both sides have to be equal. Okay. So we actually say three things there with just this one line, which is why sometimes people talk about math being a language and having it be sort of the ability to translate meanings, I guess, more directly. And that's what we're doing here. The single boxed equation is saying these three things. It's very important that you understand this. F of a exists. The limit exists as x approaches a, and the two things are equal. 1 and 2 are equal. Okay? Very, very important. Just to re-emphasize, this is a local property. So f is continuous at point A. At A. If f is continuous at every point, then I'll say it's just continuous. But if I don't say, but in general, we're going to say a point. When that does not happen, then we say f is discontinuous at A. Okay? And they say here, physical phenomena are usually continuous. For instance, the displacement of velocity or velocity of a vehicle varies continuously with time. So, as does a person's height. Yeah, that makes a lot of sense, right? Your growth, right, is continuous, meaning if you only measure yourself within like 2 or 3 days, then you expect your measurements, your height measurements, to be kind of like the same. So whenever the measurements are close enough, then the results of the measurement are, very close as well. Does that make sense? The time in which you take the measurements, right? If I measure myself today and measure myself tomorrow, then I expect both those to be very close. Or if I measure myself now or within an hour, I expect the results to be very close, right? Measure my height, I mean. They talk about discontinuities when we have like electric currents. That's very common too. Whenever there is random events, there's also discontinuities as well. Whenever stuff is random. And this is an important idea for us to be able to continue without having to, think about that definition using limits all the time. The idea is that the graph of a function can be drawn without removing your pen from the paper. If you can do that, then intuitively you can say the function is continuous, which again makes sense. So this is a continuous function. However, something like this with an asymptote here, it's not continuous. And that's because I can't connect these two halves because of the asymptote. I can't put them together. So this function is discontinuous, and it's continuous at a given point, right? At whatever x equals a, this point is. It's continuous at a. It's not continuous because it's discontinuous at a. To say it's continuous is to say that it's continuous everywhere, at every single point. Okay? Okay, keep going. Figure 2 shows the graph of a function at which numbers is f discontinuous and why. So first of all, I'll start at 1 here, right? So f is discontinuous at x equals 1, and that's because f of 1 does not exist. Okay? It had to exist. The limit exists, right, as x approaches 1, but f of 1 does not exist for it to be equal to the limit, right? So that's the first. Another place where it's discontinuous is at 3, you can see. So f is discontinuous at x equals 3 because the limit as x approaches 3 of f of x does not exist. And that's because you have a left limit being negative and a right limit being positive. So the limit does not exist. Okay? So remember, we had 3 different things that we needed. We needed the limit to exist, we needed f of x to exist, f of a to exist, and we also need both of these to be equal. And that's the reason why f is discontinuous at 5. And that's because the limit as x approaches 5 of f of x, you can see that this is here, right? We talked about this. The limit does not care about the value at the function. So this is what the limit is. We don't have a y-coordinate for it, but that's that height here, right? But it's not the same as f of 5, which is way over there, right? So each of those fails the definition of continuity for a different reason, right? Okay, so let's go and talk about this again. We can't even talk about continuity at 1 because f of 1 does not exist, so f is discontinuous. We can start talking about continuity at 3 because f of 3 exists, this is negative thing. However, the limit does not exist because from the left you get a negative limit, from the right you get a positive limit. So the limit does not exist as x approaches 3. For x equals 5, the limit exists, right? Because on both sides you get the same height there, right? F of 5 exists because you have like a little filled in circle over there, but these two are different. So the limit does not exist. Okay, so we need 3 properties for the limit to exist. Here's another one without graphs now. How we do this without graphs. We have to look at points where the function would possibly be undefined. So for example here, I'll stop saying like f is discontinuous. I'll stop writing that so it doesn't take me that long. So I'll just say it's discontinuous at x equals 2, and that's because f of 2 is undefined. You cannot plug in 2, right? Because the bottom here is x minus 2. You can't have x minus 2. Even if you could like cancel it out with something from the top, after factoring, you're not allowed to plug it in. Now B, the only place where it could possibly be discontinuous is at x equals 0, right? Because it's where the rule changes. So you have a function, and that's, let me just tell you graphically what that looks like. Right? 1 over x squared, right? Should be something like this. But then I have a hole at 0. Oh, I don't have a hole. This is just undefined at 0. And then I place a 1 over there. Right, do you see that this guy has an asymptote at 0? This is undefined, so as x approaches 0, this gets larger and larger. So, and that's because limit as x approaches 0 of f of x, that's plus infinity, which is not the same as f of 0, which is 1. Okay, so they differ. Same thing for C. Whenever I have a multi-part, like a piecewise defined function, then you have to be careful with this point where the rule changes. Okay. So I don't know what this thing is, but I'll try and see what's the limit of f of x as x approaches 2. So I don't know what the answer for this is, so I'll figure it out. So the limit of f of x as x approaches 2 is the limit x approaches 2, x squared minus x minus 1, sorry, minus 2. Let me zoom in because I think maybe that helps you. Over x minus 2. So the reason why I'm using this is because when x approaches 2, x is very close to 2, but it's not 2. So I can use this rule here for when x is not 2. Okay? So I can factor the top. And the top is going to be x minus 2. So I'm looking for numbers that multiplied give me minus 2. And added give me minus 1. So I think that's what it is. If I'm wrong, please feel free to correct me. Let me know later. But I can then cancel these out. So now I'm allowed to plug in 2, right? Because there's no issue. And that's a 3, right? When I plug in x equals 2. However, f of 2 equals 1. So f is discontinuous at x equals 2. You know, when you're doing your homework or problems, you just write all the letters. I'm just trying to save space. You can say f is discontinuous at. Just trying to save space and time here. Oh, this is a good one. If you don't remember this function, this is sometimes called the step function or the greater integer function. Many different names, but basically this is giving you, sometimes called the floor function as well. This is giving you the highest integer that's smaller than your input. So f of 5.5 is 5. So basically just round down to the highest integer. So like f of 5.321, that's 5 as well. F of, doesn't really matter, right? Like 17 point, just making numbers up. Okay, so basically just get rid of the decimal part and you get the just whole number part. I'm going to scroll over because I have graphs of these and I want to use the graph for D, but then you're going to see the graphs of A, B, and C before I get there. So this is A, let's see, with the little hole because it's undefined. This is called a removable discontinuity, right? And a removable discontinuity, sometimes it's also called a hole. It's a hole. It's called removable because if you wanted, you could just fix that by moving this filled in circle up. So that's why it's called removable. It's easy to fix. Okay. This is an infinite discontinuity, right? It's a lot harder to fix, which is what I drew before. And this one is the number is D, which is f of x equals the floor. And when you do it by hand, sometimes you do this, right? The floor of x. This is discontinuous in a bunch of different places. So whenever you have a whole number, right? Let's just discuss what happens. X equals 2, for example. Okay, so the limit of x approaches 2 from the left is going to be 1, because you're going to plug in stuff like 1.9, 1.99, and you're always throwing away all the decimals, right? So 1.9, f of that is going to be 1, whereas limit x approaches 2 from the right, you plug in stuff like 2.1, 2.01, 2.001, throw away the decimal part, you always get 2 from that. So side limits are different. So f is discontinuous at x equals 2. And the same happens at every whole number. Right? So f is discontinuous at, and we use the letter z to represent the set of all whole numbers. Yeah, that's why I wanted to show you the graph first, right? So you could have a better idea. Okay? So in each of those previous cases, the graph can't be drawn without lifting the pen from the paper, like we discussed. We call those removable, basically repeating what I said before, because it's easy to fix, right, by just redefining. But the other discontinuity here is called an infinite discontinuity because we have asymptote at that point. And these are called jump discontinuities for obvious reasons. And the definition of jump discontinuity is just to say that, you know, left limit different from right limit. So we can also say, you know, side continuity or one-sided continuity. We can say f is continuous if from the left, the limit from the left equals f of a, or the limit from the right, rather, right? Switch that up. If the limit from the right equals f of a, or the limit from the left equals f of a. And then we say it's left continuous or right continuous, okay? Or continuous from the right, or continuous from the left. Okay? We say f is continuous on an interval. So let's say something like this. Would be continuous on an interval if it's continuous everywhere, but here we're only allowed at the beginning, right? We need right continuity. And here we need left continuity because f is not defined to the right of b, so we can only talk about left continuity. But that's not a major issue. We're going to see more and more examples of that. Okay, so properties of continuous functions. So the keynote property is the one we discussed first, right? That a limit of f of x as x approaches a equals f of a. But there are some properties that we can use. For example, that the sum of continuous functions is continuous, the difference is continuous, the product is continuous, and if you multiply by a constant, you also get a continuous function. More importantly, the division, right, the quotient of continuous functions is continuous unless, right, the bottom, unless possibly when the bottom is continuous, because then you have like an undefined thing to do, undefined ratio, right, an undefined quotient. Some other interesting properties from what we said: polynomials continuous everywhere. Polynomials are continuous everywhere, all of them, and they just come straight from the direct substitution property we discussed last video. And all of these properties, polynomials are nothing but sums and multiplications. So we're good on that. No, on that front there. An irrational function is continuous where it's defined. So unless possibly at the bottom, or at the denominator, at the zeros of the denominator, I mean, right? So here's what they're saying here, telling us about a volume formula for a sphere, to sort of make you think about what that means in practical terms. So the volume of a sphere is a polynomial function. So it is continuous. So that means if you change the radius of a sphere only by a little bit, then the volume changes only by a little bit. Right? That's what continuous is telling you. Same. If a ball is thrown vertically into the air, the velocity of 50 feet per second, the height of the ball is given by this formula. So this is a polynomial. So it's continuous with respect to time. So if I take, say, two successive pictures, very close, right? The pictures are very close to each other in time, right? Then the height of the ball measured in those pictures is going to be pretty much the same. If I change the time in which I take my picture by only a little bit, then the height of the ball only changes by a little bit. So that's what continuity is telling us. Okay? Let's take a look at this example here. How do we handle this? We're going to try and see if this thing is continuous or not, or rather just find this limit. All we have to do is to see if we're allowed to plug it in, right, to use the direct substitution property or not. So we say f of x, x cubed plus 2x squared plus 1 over 5 minus 3x is a rational function. Remember, rational functions are divisions of polynomials, right? Quotients of polynomials. It's a rational function, and it's defined everywhere except at the zeros of the denominator. So 5 whenever this equals 0, right? So that's telling me 5 equals 3x, 5/3 equals x. So the only place where f is discontinuous possibly, not possibly, for sure it's discontinuous, right? Because it's undefined there, is that x equals 5/3. But that's not what I'm being asked about, right? So I say f is continuous at x equals minus 2, and the limit as x approaches minus 2 of x cubed plus 2x squared minus 1 over 5 minus 3x, that equals f of minus 2. So I just plug in minus 2 into that expression, so I get a minus 8 plus 2 times 4 minus 1, 5 minus 3 times minus 2. So that 8 minus 8, minus 1 at the top, minus 1 at the bottom, or plus 1 at the bottom rather. Let me double check that, because that's a 5 plus a 6. Oh, so it's an 11. So that's what we have. Okay? So I can just plug it in as long as I'm able to check that the function is continuous. Okay? Okay. Good news for you if you're seeing continuity for the first time. Most functions that we use are continuous. For example, sine and cosine that we studied extensively in Math 142 if you took this class. Sine and cosine are continuous, right? Remember that we discussed in Math 142, cosine is like the shadow of this point right here. If you change the angle by just a little bit, then that point, that shadow, changes by just a little bit. So we can easily tell that this is a continuous function. Same for sine. Okay? Yeah? So we have limits there. The issue that we have is that tangent is sine over cosine So it is continuous everywhere except when cosine equals 0, just like with the rational functions. So we have a bunch of discontinuities at the points where cosine equals 0 for tangent. Okay, and these discontinuities are discontinuities where f of a is undefined. F of pi over 2 for tangent is not defined because you can't divide by cosine of pi over 2 because cosine of pi over 2 is 0. Okay. So basically what we're saying is polynomials, rational functions, root functions, trigonometric functions, they are all continuous. Sometimes these are called transcendental functions. Maybe you recognize the word from the title of the book. There are more transcendental functions than just these, but these are transcendental functions as well. Okay, so all transcendental functions are continuous. Okay. Compositions of continuous functions are continuous. Right? So this is what this theorem is saying. Composition of continuous functions are continuous. Again, all of this we can prove by using like epsilons and deltas, like using the definition of limit. I don't think it's interesting for me to show you this, but if you go into a STEM course or something, maybe you should go and read the proofs. I think we have proofs in the book. So that would be interesting for you to read. Okay, so there you go. So if f is continuous and g is continuous, then the composition is continuous. Just have to be careful when you say where, right, the function is continuous. So g is continuous at a, f is continuous at g of a, right? Because now g of a is the argument of f, is what you plug into f as g of a, right? So this is continuous, right? Okay. Now, what do we do with this, right? Here's the intermediate value theorem, the first sort of usefulness that we can find in general, like mathematical investigations. Suppose f is continuous on a closed interval a, b, and n is any number between f of a and f of b, where f of a and f of b are different. This is like just technicality. We're going to discuss more. Exists a number c such that f of c equals n. I'll explain this better. So here's what this is saying, right? We have A and we have B. We're told, let's say this is f of A, and let's say this is f of B. So all we know about the function is that these 2 points are part of it. And the theorem is basically saying, let's pick any n in between f of a and b, f of a and f of b. So I'll draw like a horizontal line. The theorem is saying there has to be some point in between that has some point c, we call it c, that has f of c equals n. And why is that? Because f is continuous, we must draw the graph of f without lifting the pen or the pencil from the paper, right? So we start at this point, we have to connect it to that point. We got to connect these 2 points. We are forced to cross that red line. There's nothing that I can do. I can try and, force it and adjourn it, but at the end I'm forced to cross, and whenever I cross, this is going to be my c. Right? So f of c equals n. Okay? Take a second to understand what I'm trying to say. Read this. Again, maybe watch this part of the video again, so that where I explain this, and let's move on. Here's the graph where they explain the same thing. Another one. Another example. Doesn't matter if f of a is bigger or smaller. You have to cross the line because the line is in between, right? So that's what the intermediate value theorem says. It is true for all continuous functions, but not for discontinuous functions for obvious reasons, right? I could go ahead and draw something like that goes over there and then continues this way. And then if I chose this n over here, then there's no point that has f of c equals n, right? Because of the discontinuity, there's a gap. Here's how we use this, right? Let's show that there is a solution to this equation between 1 and 2. So this is a cubic function. Very difficult to solve. There is an equation for it, but it's very difficult to use and to memorize even. So we're trying to find the solution for it, but we can't really use any formulas to find like the quadratic equation. Factoring is not even a good idea. So how do we prove that there is one? Because maybe you're gonna spend a lot of time since there isn't a formula, and you're never gonna find one, right? So let's say what happens at f of 1. You even say they want it between 1 and 2, right? So f of 1. So I call it f of x, first of all. So let's say f of x equals 4x cubed minus 6x squared plus 3x minus 2. So f of 1 will be 4 minus 6 plus 3 minus 2. I just replace every x with a 1. So that will be, will that be 9 minus 8, 1. Is that right? No, that's 7. Let me do the math again. 7 minus 8, so that's minus 1. On the other hand, f of 2 will be 4 times 2 cubed minus 6 2 squared plus 3 times 2. Zoom in so the math is a little easier. The writing is a little easier to do. So that will be 4 times 8 minus 6 times 4, 24, plus 6. So that's 1632 minus 24 plus 6. So that is 38 minus 24. So that's positive 14. Okay. How does that help me? Add a page just so I can conclude the idea. I'll graph it, but in general, you don't have to graph to conclude if you're using the intermediate value theorem. So here's what I know. Here's 1. Here's 2. I know f of 1 is negative 1, so it's below the x-axis. I know f of 2 is 14, so it's above the y-axis. That's all I needed to know, because now that I'm forced to connect these two things, I don't know what it looks like, but I know that it has to cross the x-axis, okay? And this is going to be wherever it crosses is my solution, right? Because we want f of x equals 0, right? So I just have to verbalize that now, and I'll be done with the proof. So I'll say, by the intermediate value theorem, there is some c between 1 and 2 such that f of c equals 0. And I'll say, which means c is a solution. C is a solution, which is what we're looking for, right? We're looking for a solution of the equation. Let's say solution of the equation. Okay? This is very powerful, very interesting idea, because now we know that there has to be something in there. And you can think, this is not that good, right? Maybe we don't know what... We know it's between 1 and 2, but how does that help me? You know, what if x is in millions of dollars? How does that help me that in between $1 million and $2 million I'm able to solve this problem that I'm looking for, that I'm looking to solve? There's a wide range is what I'm trying to say, right? There's a huge difference between 1 and 2. So what you can do, if you want to narrow down where the solution is, you can try and see what's f of 1.5. Yeah. So actually calculate and see what's f of 1.5 so that I can make my point across. So it's going to be 1.5 cubed minus 6 times 1.5 squared plus 3 times 1.5 minus 2. Let me double check to see if I did the math, if I typed everything right. I think so. So that's actually, so this is the end of my proof, right? So I draw this little square, or I say as we wanted to show, or QED, sometimes it's something people put there. I'm just expanding the idea now. And I'm saying now that f of 1.5, if I wanted to find out, that is 2.5. So 2.5. So look, between 1.5 and 2, I have two positive numbers, so there's no guarantee that this crosses the x-axis. However, between 1.5 and 1, right, I have one negative number, one positive number, so it's forced to happen that way. All of a sudden, I had a 1 sort of tolerance, right, possible error. Now I have a 0.5 possible error, and I can keep doing that. I can see what's f of 1.25 go in between. So I can keep cutting the interval in half and decide which half I want to work on, and I can solve this equation or find a very good approximation of the equation if I want, of the solution if I want. It's a good idea. Whenever you see like repetitions like this, you can think that that's usually how computers solve these problems. Okay? Try and understand what I'm trying to say, and review this if you need. And here's what they're trying to show us. They're showing the graph of f in between -1 and 3, in the view rectangle between -1 and 3 for x, and between -3 and 3 for y. You can see that the graph crosses the x-axis between 1 and 2. Actually choose all the way over to 14, right? But you can see that it does cross way before. We're also able to find out that 1.5 was also positive, so we got a better approximation than the slideshow knows about, right? So if you zoom in even further, right, it's like I was saying before, it's between 1.2 and 1.3. So if I wanted to get a better approximation, I could plug in 1.25 and I get right in the middle here, and it would tell me that it was positive, and then I'd know that it's between 1 and 1.2. So I can keep repeating this idea. So this is in general what we're being told, right? A computer calculates a finite number of points on the graph and turns on the pixels that contain these calculated points. So the pixels are the little dots on the screen, right? So we are assuming that the function is continuous and takes on all the intermediate values between those consecutive points. So it assumes that the function is actually continuous and that it behaves nicely between these points. We can try and trick a computer if you want, but the computer just connects the dots and turns on the intermediate pixels by, assuming the function is well defined in there. I guess this is just a good way to end, so I'll stop here. Thank you for watching this video, and make sure that you understand this idea. This is a very powerful and important idea.